does all this mean? So I'll tell you what I told the last section, and this is really important. All of this code is worthless, okay? There's almost no value in this code that we've written on the board. You can take notes on it. It will not help you on a test. It will not help you when you're writing your programs. Those are the senses in which I say this is almost totally worthless. What's worthwhile on these boards is this picture of your structure and the way that we manipulated it to do things like insert a 25 into the list. Okay? That's where you want your focus to be when you're trying to figure this stuff out. Not, why did I say next node equals list next node dot next? Okay? This is an interpretation in C of an algorithm that we were doing on the board. I want you to try to understand the algorithm. I want you to be clear if you see a picture of your list and someone says, I want you to delete the 30, that you know what would change in this array. Okay, and you'll actually have questions on midterms or finals about this. No code anywhere in sight. You'll have something like this or a memory map, and I'll ask you to do some things to the data structure, devoid of any C code. So this is your challenge, is to understand the concept of a linked list. The idea that your node points to the next node, and if you want to insert something, you've got to sandwich it in between, so you have to change this pointer to point to your new node, and your new node points to what used to be the next node. Once you understand that, the code almost comes out for free. Right? Once you really understand that what you want to do is take your new node and have that point to whatever next node is, list bracket new node dot next equals next node. Right? And the first few times you write this, it's confusing as heck. But once you've done this and you sort of have internalized what's going on here, this stuff comes out immediately. Right? The whole challenge is in the data structure itself. And that's the essence of this course. It's a data structures course. So we're going to be working with linked lists and trees and hashes and things like that. And your goal is always to try to understand data structure. We're going to be implementing these in C, but the better you understand the structure, the easier the implementing is going to be. And sometimes there'll be some tricks. And when we do programming assignment 2, we'll work with dynamic memory. And we'll have to learn some mechanics with malloc and free and pointers and addresses and such. But this is the bulk of the challenge, okay? So I want you to think about this, and I want you to get used to drawing pictures and working on large, clean sheets of paper with a good eraser, preferably a pencil, and making manipulations to these structures. And this is what you'll do when you're debugging your programs. You'll write your code, and you'll insert something, and you'll look at your list, and it's not at all what you expected. And the only way that I know of to figure out what's going on is to go back to this. Go into GDB, look at your list, make a picture, and then fix in your mind, what should my delete routine be doing? It should make this change, and this change, and then step through your code. And every time that your code touches this, look at this in memory, using the debugger, and see if it agrees with the picture that you drew. And at some point it won't. And that's an aha moment. And that's where you learn, oh, I was using the address, and I should have been using the thing pointed to by the address, or whatever. So don't get hung up in the code. The code is valid pseudocode, okay? But we've left off lots of details. But this is not how you'll learn what the linked list is, right? This is. And this should be derivable from this. All right, does that make sense?
I was just wondering, when Scott had us doing the linked lists, we had a next and we also had a previous.
Mm-hmm.
And so I'm wondering if that's something that's useful here or not useful and why.
It is, and we're not going to do it in PA1. But this idea that if we start going through the list and we come down to here and this is bigger than 25, so we want to insert before this node, we needed to sort of keep track of the previous node and the current node. We can make another kind of thing called a doubly linked list, And each of these will have the index of the next node, but also another entry for the index of the previous node. And with that kind of structure, we don't need to keep track of where we were and where we are. We can just look at where we are, and we can always back up by looking at the previous entry. So that takes a little more memory, but it simplifies your coding. And if you're processing your data in a way that needs you to go forwards and backwards, doubly linked lists are really nice. So this one, we're just using a singly linked list.
Can I get that signature?
Yes. That's okay. It's a prereq.
I already got the override in.
Okay, I'll initial that. I don't think I need to initial anything else. Cool.
Thank you.
All right. Super. All right, so what about the edge cases? The trickiest part of working with linked lists is usually the edge cases. Dealing with an empty list, dealing with a full list, putting something in the beginning, putting something at the very end. And those can trip you up. So let's rethink this algorithm a little bit in terms of what can go wrong. So let me simplify this. And let's suppose our list only has two elements in it, a 10 and a 20. And let's suppose our sentinel points to index 1, that's our 10, that points to index 2, which is our 20, that's our my null. Everything else is invalid, we don't know what the data next fields are. So here's a two-element list, 10 and 20. And we want to insert a 30. All right, back to our table, devoid of code. Start at the index, this is our current node. The next node is 1, so this is next. 10 is smaller than 30, so let's move. This is next. Next data is 20, that's smaller than 30, so let's move. This is next. Let me back up. All right, this is next. Next data is 20, that's smaller than 30. So we want to move on to the next node. But if we do that, this is going to become index 2. Next is going to become index -1. And if we try to use list bracket next, we might segfault. So once we see that next is -1, we know that we're at the end of the list. So we need to put something in here as follows. So this equals, if list next node data is less than new num, set this equal to next node. So I'll put this over here, and I'll set next node equal to list bracket next node dot next. So list bracket next node dot next is -1. So next is pointing off somewhere in limbo, it's -1. So at this point, I'm going to do something. I got to check to see if next is -1. If I don't do that, and I come up here, I'm going to segfault on this when I try to check element next node of list. So, so next node is -1. So I'm going to say if next node equals -1, and I've got a comment here saying I'm at the end of the list. So how do I insert a new node at the end of the list? get your node, store your new number in here, make sure it's valid. Take this node.next and set it equal to the index of your new node, and set your new node.next to be myNull, to say that's the end of the list. So this code in here is new node equals get node list. List bracket new node dot data equals new num. Same as we did over here. List bracket new node dot next is myNull. Right, so we got a node, this became valid. We put a 30 in here. We set the next field to myNull, which is -1. And then we take what was the last node in the list, which is this. So list bracket this node dot next, and we just set that to point to whatever new node is. So that sets this to a 3. And we're done. Again, the code's getting sloppy and squeezed in and hard to read. It's not essential. Right? After we've adjusted this node and next node, if next node is -1, we know our new node's going after whatever this node is. And so we just adjust this to point to our new node. We set our new node's data to our new data. We set new node's next to myNull, and we're done. We've inserted at the end of the list. Last edge case, what happens if you want to insert in the beginning? So let's insert a 5. This is always interesting because I really don't know what's going to happen in any of these cases. I'm doing this as we go. So let's insert a 5. So this node starts off at 0, and next node is this node's next, so that's a 1. So we check list next node dot data, that's a 10. It's not less than 5. So we're going to kick out of this loop, and we're going to go ahead and do our insert code. I wonder if this is going to work as is. It just might. So we'll call get node, which will give us a 4. So this is new node. We'll set list new node data to our new data, which is 5. Get node made that valid. List this node dot next equals new node. This node is up here, set its next field to new node. This becomes a 4. Oh, new node data, yeah, that's a 5. And then list new node dot next. So new node is 4, so this next field should be equal to whatever next node is, which is a 1. This becomes a 1. And we've inserted our 5. So now our list begins with node 4, which is a 5, followed by a 10, followed by a 20, followed by a 30, end of the list. So there's no special case in the beginning. Last special case, empty list. So let's go ahead and start with an empty list with your init routine set up by making this a -1 and clearing all the valid flags. So this node equals 0, next node equals list bracket 0 dot next. So next node is -1 right in the beginning, segfault. So this test I would actually do up here. And we could write it separately up here, or we could rearrange this so that it happens at the top of the loop if we're clever. But let's just look at this code. If next node is equal to -1, we're at the end of the list. So get a new node. So new node is going to be a 1. That's going to be valid. And we're All right, so new node equals get node, so that's a 1. List new node dot data equals new number, so there's our 42. List new node dot next, so new node dot, sorry, 42 here. New node dot next, which is over here, should be my null, so that becomes a -1. And list this node dot next should equal new node. This node is 0, so that thing's next should equal new node, which is 1. So is this a valid list? Sentinel is 0, points to node 1. 42 is the first thing in our list, that's the end of the list. So that works. If you do this really, really, really just right, you can avoid all special cases. Don't worry about making that happen though. I think it's more useful to have to code up the special cases because then you understand what's happening with an empty list, inserting at the beginning, inserting at the end. Rather than stumbling across or seeing the one magic way to write your while statement with 2 things in the while that makes all of this work without any special cases. But this is how you develop this code, right? Make a picture of it and go through these manipulations. And if this didn't work, if this somehow didn't insert my node in the beginning, I would put a special case up here, right? And I would say if in the very beginning, if list bracket this node dot next equals -1, and just write code to do what you have to do in that case. Right? It's your machine, it's your code. You get to tell it what to do. And if you can conceive on paper how you would go about doing this successfully, write code to tell the computer to do that. And you've got the computer doing your bidding for you. It's glorious. All right, the other thing we did not talk about here is what happens if you run out of nodes. We call, over here we say get node, get me a new node. Remember, if we run out of space in our array, get node will return -1. New node will be -1 when we say list bracket -1 segfault. So you need to check when you're getting a new node, make sure it's giving you something valid. Just check to see if it's not equal to my null. If it is equal to my null, you're out of memory. So print out a message out of memory and just exit or something. Okay, I'm not going to use up all your memory in this program, so you don't have to worry about that. What about if your list looks like this and I try to insert 42 again? So I'll check my first piece of data is 42 and 42 is not less than 42. So I'll go on to the next piece of data and that's the end of the list. So I might end up putting a 42 in there. And if I do less than or equal to, I might insert before. And in fact, I don't want duplicates in here, right? The assignment says that somewhere in here. Yeah, so insert a number into the list provided the node is not already in the list. It should then print either the message success or node already in the list.
You can just insert an if statement in the beginning of the if statement you already have to check if the number you're inserting is the same as a number that you're checking, and if it is, just exit the function.
Cool. So if list node.data equals new num, we can just exit. There's an even easier way. What's the easier way? Think lazy.
Call search first.
Call search. You've got a search routine you're going to write. So before you call add, call search. If the node's already in there, print out a message, say it's already in there. Same thing with trying to delete a node that's not in the list. When you delete, you keep going through until you find a node. You have to make sure you don't run out of nodes, right? But if you search first and make sure the node is in the list, you don't have to worry about the possibility that you hit the end of your list and you haven't found your number, because you just called search and guaranteed that it was in the list. So these routines that you're writing can actually help you with some of the other routines you're writing. And don't be afraid to use those. Right, this is again the idea of modularizing, of code reuse, and having this unified interface. All right, questions? Let's talk about deletion. And deletion's not a whole lot different than adding. It's actually slightly easier.
Deleting by the value or the index?
Deleting by the value.
By the way, the search function, does that return the index of the found item?
No, it returns a 1 or a 0.
Just checks to see if it's in there?
Just checks to see if it's in there. Return a 1 if it's found, 0 if it's not.
Oh, interesting.
So this is a good time to discuss further abstract data types, which I mentioned in the video yesterday. And this is key to moving into object-oriented programming, like using Java, for example. We're talking about linked lists. What is a linked list? Well, for us, it's an array of these structures that have 3 pieces to them, where the next field points to the next element. That's not really what a linked list is. That's our implementation of a linked list. Okay? A linked list is a collection of numbers with a beginning of the list, a notion of immediate successor. Each element has a number that comes immediately after it, a notion of an end of a list, and routines to allow you to do things like insert a number into the list in order, search for a number, delete a number, initialize the list, print the list. That's what a linked list is. Nowhere in that long run-on sentence that I just said did I mention arrays, negative ones, pointers. Okay? In fact, we can implement that linked list using this array-like structure. We can implement it using a single array of integers instead of an array of structures. We can implement it using dynamically allocated memory. We can implement it with hot dog buns and toothpicks. Okay? The linked list implementation is different from the notion of what a linked list is. So when we talk about linked lists, we're thinking of what's called an abstract data type, an ADT. And an ADT is basically a description from a high level of what this data structure is. Okay, for example, a stack is, yeah, we did stacks in 270. A stack is a collection of numbers that you can push something into the beginning of, and when you say pop, the thing that you last pushed is what you first pop. So it's a first in, last out, or a last in, first out, same. And it has a notion of being empty, and it has a notion of being full. Lots of different ways you can actually implement that on a computer. You can use arrays, you can use dynamic memory, you can use arrays where you increment when you push, decrement where you push, and so on and so forth. But as an abstract entity, it's just this collection of things. The last thing that goes in is the first thing that comes out. It can be empty, it can be full. Okay? So these routines, add, search, delete, and so on, are our interface to this linked list. And they totally don't care about this stuff, right? Which means that when you're writing a program to use this linked list, you download this from the web because you want a linked list, you don't have to know anything about this. All you need to understand is those 5 routines. Call init to create the initial list, call add to add something, call search to find if it's in there, and so on. And when the new version of this comes out and is released and you download it and relink your code should not change. The new version may be doing something totally different. It may be a new improved version that doesn't run out of memory after 100 things are in your list. It has the ability to grow indefinitely. And you don't have to change a single thing in your code. You just recompile. Okay? That's the goal of an ADT, because that gets us into code reuse. And it means in Java in particular, we can use any of the tens or hundreds of thousands of pieces of code that have been written for us and know that each time that a new version comes out, our code is still going to work and presumably get better. All right, you asked something that started this whole, and I don't remember what your question was that caused me to launch off onto this.
It was whether or not the search returns an index of just.
Yes, yes.
If 0 is always going to be the sentinel in our particular structure here, I mean, wouldn't anything other than 1 or other than 0 be it's found?
No.
Like, couldn't you return an index and you could just use it if you want to, and then otherwise?
You could. And you might be able to do that, except that the person using this is going to look to see if the answer is 1. If it's not 1, they're going to say it's not found. Now, I could have written this more cleverly. I could have said 0 if it's not found, non-0 if it is. And I could be returning the index to you. And I might not tell you that, but you might discover it, right? And as long as you understand that if it's non-0, it means that it's found, your code and my code are going to get along great.
It's like when we discover those extra little handy tricks like, oh, this actually returns a Boolean.
Yes. Or string compare returns the difference in ASCII codes of the first character that doesn't agree.
Yeah.
Right? But if I change things at some point, right, and I end up returning 3 times the index of the thing, and you're trying to do something other than what's specified here with it, suddenly your code may stop working. All right, so that was a good launching point for abstract data types. All right, so so what were we going to do? Deletions, right?
Yeah.
So let me simplify my list again. Really, you can't have enough big sheets of paper and good erasers and pencils for this stuff. It really helps. It sounds silly, and you might be able to get by with a little corner of your napkin, but it really helps. And you actually end up going back to some of these things sometimes. And it helps you get fast at doing this when you're like doing it on a test. All right, so sentinel node, first node is 1, that's a 10, second node is 2, that's a 20, third node is 3, that's a 30, and that's the end of the list. So our list looks like this. So let's delete 20. Again, I would call search first and make sure 20 is actually in the list. That simplifies our code. So we call search, search comes back with a 1, we know there's a 20 in here somewhere. So I'm going to say this node starts off at 0. And let's just think through this. If I start off here, next node is 1, check next data, is at a 20, no. So I'm going to move down to this node, check next node's data, is it a 20, yes. That tells me that I need to delete this next node. So I'm going to do this with just one pointer, I think. I'm going to start off with this node equals 0. And I'm going to say is the next node the node that I want to delete. I know I never want to delete the sentinel, right? The data in the sentinel node is not meaningful. So I'm going to say is list bracket this node dot next. that may be too many brackets, depending on the time of day. What?
Don't you need
Dot data, yeah. What is this saying? Look at this node in the list. Look at its next field. So this is the index of the next node. Look at that entry in the list and check its data. So this is the next node's data. Is the next node's data equal to the thing you want to delete? Now, if you don't like this, right, do something like next node equals list this node dot next next data equals list next node dot data is next data equal to the number.
Is this a game sometimes we play of how much of our code can we put in one line of code?
Yes, absolutely. Yeah, and there's contests for, you know, most convoluted one-line program. But I like this, right?
Yeah.
Unless I'm hyper-caffeinated or something, I don't want to have to think too hard, right? I'm in for the long distance.
It's like studying for a test every time. Oh.
Yeah. So let the computer do some of the work for you, right? Here's a variable that tells me the next node. Here's a variable that tells me the data in the next node. Let's see if that data is the thing I want to delete, right? Later on, you know, you can take it and you can rewrite it like this if you want. Or if you think of it like this naturally, that's cool. So one way or another, decide if the next node's data is what you want to delete. If not, then just move to the next node. So this node equals list this node dot next, and go back here. So that's a while loop. While all of this stuff is not equal to the number you want to delete, set this node equal to the next node. And that'll spin until you eventually get to a place where the next node's data is the one you want to delete. Again, if you aren't sure that your number is actually in the list, you need to check for that in here. Otherwise, at some point, next becomes -1, and you check index -1 on the list, and you sig fault. All right, once we come out of this loop, we want to delete node list bracket this node dot next. So let me do it in this style. This node is 0, next node is 1, next data is 10. 10 is not what I want to delete. So set this node equal to list this node dot next, or just next node. So this node changes to here. Next node becomes list this node dot next, that's index 2. So next node is a 2. Next data is list 2 dot data, that's a 20. Is next data equal to my number? Yes. So I want to delete next node. The way I do that on paper is I take this node, the node that came before, and I simply have that point wherever this node was pointing. This pointed to 20, 20 pointed to 30. I'm going to change this to point directly to 30. So I'm going to replace this with this.
So next node dot next.
Yeah, so let me do it in this language first. List bracket this node dot next equals list bracket next node dot next.
And do we want to check the, flip the valid flag on the?
And then we want to flip the valid flag, which we can do by simply calling release node list comma next node. that does is flip the valid flag. No intuitive reason why we're saying list this node next equals list next node next, right? And if I had done this in a different way, this statement would look different, right? Again, this is not how you're going to understand it. This is, right? And once you know, okay, so I want to find where the next date is 20, you take that next and copy it up here, then you write your code to say that in C. So do this and return. I think this works automatically if you delete the first node. So if we're deleting the first node, this node is 0, next node is a 1. List this node next, or list next node dot data. Next data is a 10, so if we're deleting the 10, we'll come to our delete code right here, which says list this node dot next, that's this, should be equal to list next node dot next. Well, next node, right, this was a 3, so we change this to a 3. And now our sentinel points to a 30 is our first node, and that's the end of the list. So we deleted the 10. Yeah.
Really quick, what all does the release node function do? Doesn't it just flip the flag, or what
Just
all?
flips the flag. So release node resets the valid flag to 0 after you delete a node. But I'm going to be really picky and insist that when you write this, when you want to flip the valid flag to 0, call release node. Don't just set it equal to 0. Okay, I will take off points if you do that. The reason being that I don't want your main program to interact with this, but I don't want your lower level code, your add and your delete, to have to tinker around with this -1. I want that to be happening only inside get node or release node.
Okay.
So I need to add a comment to get node. I'll put that in tonight. I need to mention that get node should set the valid flag to 1. I want that to happen here. So I will. Do I say that? I know I keep saying it verbally, but I think I forgot to actually put it in.
No, it doesn't actually say it. So those are the only two parts that I'll never support, so.
Yeah, those should be the only 2 parts where you have to monkey with the valid flag. And so your init routine can use release node to set the valid flags to 0. Your init routine can actually set the first one. So this flag here is kind of optional, it's up to you. It's more consistent if you set this to valid, but you know that index 0 is always a valid sentinel node. So you don't really need to use this as long as when you're checking for an invalid block, you start from index 1 instead of 0. So if you want to set this by hand, you can do that in your init routine. But I don't check it to see if it's valid.
And the get node does return the index?
Get node returns the index.
Okay, just making sure.
Mhm.
Oh, yeah, there it is.
And if there's no space left, it returns -1, my null.
One more question. When we're doing the .h for declaring out what a node is, just to make it easier, can we type def that?
Sure,
Okay,
yeah.
perfect.
Yeah, as long as you have a struct node defined, because that's what my code will be looking for. But if you type def it, it's going to be the same thing.
Okay.
Yeah.
So, like when you pass stuff to it in the SS, if I just call it node and type def it as node,
That should work fine.
so I don't have to type struct nodes
Mhm.
exactly, as long as it registers the data type.
Exactly.
Okay.
Yeah, that should be fine.
Cool.
Talk about print. Print is deliciously easy after all of this. list. Well, let me change this first of all, because we've trashed our list into nothingness. All right, so there's our list with 10, 20, 30 in it again. So how do we print? Well, we start off with index 0. And if next is -1, we're done. If this is a -1, there's nothing in our list. We don't have to print anything. Otherwise, move to this node, print out the data. And check the next. If the next is -1, we're done. Otherwise, move to this node, print out the data. And check the next. So, this node equals 0, while this node in other words, while we have another node, so while the next node exists, this equals list this node, equals list this node dot next comment, this is the next node, kind of silly since it's called this node, and then print list this node dot data, and that's the end of our loop. So start with the sentinel. If the next node exists, move to that next node, print out the data. Look at the next node after that. If that's not null, move to that new node, print out the data, and so on. That should work on an empty list. It should work on a non-empty list. And you'd like a print routine sooner rather than later because you can use it to debug the rest of your code. For example, if you have a print routine, you believe it, you can call your add routine to add a number and then call print, see if the number is in the list. Add another number, call print again, see if it's still in the list. See if they're in the right order. Okay, as long as you believe that your print routine is correct. If your print routine has problems, you might be trying to debug your add routine, and the problem's in your print routine, that's a problem. So make sure this is working. How do you do that? Build a list by hand. Make an array and just explicitly set up some of the values to make a list with, say, 3 things in it. Call your print routine, make sure it prints. And there's not as much that can go wrong in here as there is with, say, delete or insert. Print is usually pretty straightforward. And the last thing is search, and search is as easy as print. Right? Instead of printing this out, if list this node dot data equals desired number, you're done. Return 1 and say, hey, I found your desired number in the list. If you get to the end of this loop and you haven't returned, you did not find your number, return 0. So print and search, really, really close. Instead of printing, we kind of print into our mind's eye and we compare it to the number we're looking for. And if we found a number, we just exit right there and say, found the number. When we get to the code that normally says we're done printing the list, we know we didn't return, so we didn't find the number, so we return a 0.
In our main function, when we're calling these, I don't know why I can't remember, but when we pass a node to it, do we do ampersand then the name, or do we just put in the name of the node?
So you never pass nodes to these things, you always pass the list.
I'm sorry,
Which is
yeah,
an
we're
array of
passing
nodes.
nodes.
So in our main program, right, so you declare your list like that.
Right.
So we'll do something like init list, add list, comma 5, add list, comma 10, print list, and so
Okay.
on. And when you say list, because it's an array, it's actually a struct node pointer, which is what these routines are expecting.
So when we're in our functions and we're writing this code, we don't use the period, we use the arrow.
Probably not the arrow. Because when we're in our code, like down here, list bracket this node, this is a struct node. And so to get the next field of this struct node, you use a period. List is a pointer to a struct node, but list bracket something is a struct node. So it's just like saying struct node x, x dot next, x dot data, x dot valid.
Okay.
This is preamble to programming assignment 2. Programming assignment 2, we're going to do the same thing, but we're going to do it with dynamic memory. But this keeps us from having to talk about dynamic memory and deal with pointers and addresses and arrows and things like that. But once you're done with programming assignment 1 and you understand how your code works, it's going to be really easy to change it into programming assignment 2. So after you turn it in, don't like rip up your code, because you'll get to use it again. But it'll be a few tweaks, almost something you can do mechanically to change this into PA2. And PA2 will actually use dynamic memory instead of an array, which means we'll have a linked list that can grow arbitrarily large until we run out of memory on the machine. And that'll be nice. And that'll be our launch off point for other data structures that'll look similar. All right, that's how you do your program. So get node, just start at the beginning, find a node that's got valid equal to 0, set the valid to 1, return that index. Release node, just set the valid to 0. And then the main program, let me take a few minutes and talk about the main program. And I don't want you to get bogged down on the main program, which doesn't mean you won't, you might. But I want you to spend most of your effort on the data structure itself. So what are we doing in main? We're processing a series of commands. So you want to print a prompt. So printf and if you don't do that \n, this will print a greater than sign and it will sit there. So that tells the user, hey, it's your turn to type something. So it prints a greater than and it waits and the user types something in. And then let me see if I actually wrote this. It's possible. Oh, I didn't actually write it. Alright, I'll have to write this eventually and I can tell you what it does. So you want to read a line from the user, right? They type something and they hit enter eventually, and you want to process that as a command. So the user may type something like I space 5, followed by enter. Okay, here's what I'm going to say is the best way to ingest this. Use fgets. So make a character buffer. that says let the user type something until you've either got 120 characters or they hit enter. 119 characters actually. So they'll type something in, hit enter. Buffer is a character array that contains I space 5, new line, and a null terminator. All right, or it may contain D space 3, or it may contain search space 7, or it may contain just the letter P. It's one of the commands, okay? Or it could be something that's not one of your commands. All right, suggestion for how to process this. Look at the first character and decide, is this an insert, a delete, a search, a print, something I don't understand, an exit, whatever. How do you find the first character of their input? It's just buffer bracket 0. So you could do something like if buffer bracket 0 equals quote I. If the first character is I, then presumably they type I followed by white space followed by an integer. What you need to do next is figure out the value of this integer. That's where scanf will come in. So you can do the following. scanf buffer, quote, I space %d, address number. And if buffer looks like I space and an integer, the value of that integer will now be in this variable called number. But if they type I space ha ha ha, ha 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 will not parse correctly as an integer, and there's no telling what's going to be inside number. So scanf returns a value that tells you how many things it converted. We're asking it to convert one integer, so this should return the number 1. So let's put this into a variable. Result equals scanf. If result equals 1, user entered I space integer. Now we know that they entered an insert command, they typed in a valid integer, and the value of that integer is in number. Bang, easy. All your add routine. Else. Down here, it means that they typed an I, but it was not followed by an integer, so put out an error message, or a usage message, or something, whatever the assignment asks you to do. Else, if buffer bracket 0 equals P, go ahead and do stuff. And if you don't like big, long if-else statements, use a switch statement. Right? Switches work great for these kinds of command line interfaces. So if you don't know how to use switch, go ahead and look it up. And I recommend it. So switch on buffer bracket 0, and you can say case I, and list everything it should do if it's an I, case P, list everything to do if it's a P, and it nicely organizes it without getting into a whole bunch of nested if-else, if-else, if-else. You're on, right?
Yeah,
Okay.
I know there was a room change, maybe it didn't get set up correctly.
No, we go until 2:05, so I cut out early, but it's usually pretty close to 2. And I didn't realize it was almost 2.
Good.
So we are out of here. Okay, have fun with that. I will post the video. If you have questions, go ahead and start a discussion topic.